In this video, we will recap the chain rule of calculus for both scalar and multidimensional data. You should already be familiar with this, but since this is a key concept in this lecture, we will brush up on some of these details. So let's dive right in. Recap of the chain rule of calculus. So the chain rule of calculus allows us to compute derivatives of compositions of functions in terms of their individual derivatives using a product of their functions. So if we have two functions, let's say g of x and f of y, where f of y uses this first function g of x inside, so we basically call this a nested function. Then the chain rule of calculus states that the derivative of the composition of these two functions, so we denote derivative as the prime here, and the composition of these two functions with the circle. So here the dependency of the function f is on the variable x through this other function g. So we first take the derivative of the outer function of f that gets the argument of the function g of x, and now we multiply this with the derivative of the inner function g of x, so which is like g prime of x. So we can also write this in this so-called Leibniz notation. For that, we will set y to be the function g of x, and here z to be a function f of g of x or f of y. So again, the dependency of f on x is through the function g. Then we can calculate the partial derivative of z with respect to x, as then the product of first deriving z with respect to y, and then multiplying this with the partial derivative of y with respect to x. So this is equivalent to the partial derivative of f of g of x with respect to g of x times the derivative of g of x with respect to x. So just as the above, we could write this as f prime of g of x. Basically, we can write this as f prime of g of x times g prime of x. So again, the derivative of the outer function times the derivative of the inner function. So to make this a little more concrete, we have this little example here. So we have the function y is equal to g of x as sine x, and then we can write z as f of sine x as this composition function, as then the natural logarithm of y, or the ln of y. So the outer function is the ln, and the inner function here is the sine. Now we want to compute the partial of z with respect to x. Observe again that the dependency of z on the variable x is through the function g. So we take the derivative of the outer function ln with respect to its input, which is the sine, and then take the derivative of the sine with respect to x. So here the derivative of the ln, which is then f prime of a, is just basically 1 of a. So we can write in general f prime of a is just then can be written as 1 of a. So then here we write 1 by sine x, which is the argument for the ln. Then the inner derivative is the derivative of sine of x with respect to its input. So that will be the cosine of x. So now we compute the derivative of ln of sine x as the composition of computing the outer derivative with respect to its input, and then multiplying this with the derivative of the inner function with respect to its input. So we can use the chain rule not only for scalars, but also for vectors or matrices. So for instance, if we consider a vector x having elements Rm and a vector y having elements Rn, and then a function g that is mapping from Rm to Rn, and then let's say another function f that is mapping from Rn to R, then we can also say that y is equal to g of x and z is equal to f of y. We can then calculate the partial derivative of g with respect to one of the components of x. So the partial derivative of z with respect to xi, then as the sum of the product of taking the partial of z with respect to each individual component of y, that is then directly dependent on. So we loop over the j's that we see here, which and indexed different components of the vector y, and then it is multiplied with the partial of yi with respect to xi. So this can also be written in a more compact way using the vector notation. Here we want to figure out the gradient of the scalar z with respect to the components x. So this can also be written as this compact notation here. So this is nothing but just a Jacobian matrix. So the partial of y with respect to x transposed times the gradient of z with respect to the vector y. So we won't go into too much detail. So you will see this coming up now and then, like in the lecture, for example, in recurrent neural networks. So if you want to know more about this in further details, then I suggest that you can refer to chapter 6.5 in the deep learning book. Okay, so if we consider a vector y having elements Rn, and then we consider a function f that is mapping from Rn to R, then if g is equal to f of y can be basically written in this form that you see here, which is the partial of z with respect to each of the individual components of y. And then if we consider this function f of y as this, then the derivative of z with respect to y is just the vector form. So this is the vector from y1, y2, then to yn. Now if we consider a vector x having elements Rm, a vector y having elements Rn, and then a function g that maps Rm to Rn, and y is equal to g of x. This is what we saw before as well. Then we can write the partial derivative of y with respect to x, then as this n by m Jacobian matrix G that you see here.
Now, for example, if the function g represents a simple linear layer, let's say g of x is equal to wx, then the Jacobian matrix in this case is the matrix W itself. Now let's say that we have an n by m matrix W and a function h that maps this matrix to a real number z, where z is equal to h of W. In this case, we can write the gradient of the scalar z with respect to the matrix W as simply the matrix of partial derivatives of h with respect to each entry of the matrix W as shown here. Again, for example, if the function h of W is the square of the Frobenius norm of a matrix, then from above, the gradient of the scalar z with respect to the matrix W is again the same as the matrix W.
All right, so that brings us to the end of this video. I have two questions again. what is the derivative of the ReLU activation function, and what is the derivative of the logistic sigmoid activation function. Thank you, and I will see you in the next video.